Every single app you use, deep down, has a database. And that database is basically in a constant tug-of-war with itself. On one hand, it's got to be like a bank vault, keeping all your data totally safe and correct. But on the other hand, it's got to be a world-class sprinter, getting that data back to you in the blink of an eye. This tension, this balancing act between safety and speed, is really the heart of how all databases work.
So let's make this really concrete. Picture this. You're sending a friend some money. You hit send, the money disappears from your account, and then boom, the whole system crashes before it ever shows up in theirs. What happens? Does your money just vanish into the ether? How does that not happen? Well, the answer gets us to the very first promise of any good database, safety. And that brings us to our first pillar, safety. This is the database swearing an oath to you that your data is always going to be correct. It's protected. It won't get corrupted no matter what chaos is happening. Now, to actually deliver on that promise, databases follow this really strict set of rules. It's a famous acronym, ACID. That stands for atomicity, consistency, isolation, and durability. These 4 properties, they are the absolute bedrock of data safety in most of the databases we rely on every day.
Okay, first up, A for atomicity. This one's simple. It's all or nothing. Think back to our bank transfer. Atomicity is the rule that says the money leaving your account and the money arriving in the other account are part of one single indivisible operation. If any part of that fails, literally anything, the whole thing gets rolled back. It's like it never even happened. There's no dangerous in-between state.
Next, we've got C for consistency. This just means the database has to play by its own rules. So if there's a rule that says a bank account balance can never, ever drop below 0, consistency makes sure no transaction can break that rule. The database is always moving from one valid, rule-abiding state to another. It never ends up in a weird, illegal state. Then there's I for isolation. Imagine hundreds, maybe thousands of people hitting that bank's database at the exact same second. It could be a total free-for-all. Isolation is what prevents that. It makes sure that all these simultaneous transactions don't interfere with each other. It creates this illusion that each one is happening all by itself in a nice, orderly line. And finally, D for durability. This is maybe the most comforting one. It's the promise that once the database gives you the thumbs up and says your transaction is done, it is done. It's permanent. It'll survive a power outage, a server crash, you name it. That data is saved and it is not going anywhere.
This quote from the PostgreSQL documentation just nails it. A transaction is what bundles all those little steps into one big, all-or-nothing operation. That's the magic that makes ACID possible. Okay, so we've established our data is super safe. That's great. But what's the point of getting it back takes forever? And that leads us straight to our second pillar, speed. Because it's not enough for your data to just be safe. It's got to be fast. And in the world we live in now, that means ridiculously, almost instantaneously fast. So just try to wrap your head around this. You've got a database with billions of rows of data. It's all stored perfectly, it's totally safe. How in the world does the database find the one specific thing you're looking for, like one person's profile, in just a few milliseconds? How does it avoid having to read through every single one of those billion records? Well, the answer is a brilliant little thing called an index. And the best analogy really is a book. Without an index, the database has to do what's called a sequential scan. It literally reads the entire book from page 1 to find what it's looking for. Super slow. But with an index, it's just like using the index in the back of a textbook. You look up the term, it tells you the page number, and you jump right there. It is an absolute game changer for speed. And of course, it's not a one-size-fits-all thing. Just like you have different tools for different jobs, databases have different kinds of indexes. The most common one is a B-tree index, which is perfect for finding things that are equal to, greater than, or less than something. Think of it like a library's card catalog. But if you need to search for a word inside a chunk of text, you'd use something totally different, like a GIN index. That's more like a book's keyword index. But, and this is a huge but, there is no free lunch. Here's the trade-off. Indexes make reading data, your selects, way, way faster. The cost? Every time you write new data or update it, the database doesn't just write the data. It also has to go and update every single index that's affected. That slows down your writes, and it also takes up more storage space. So we've got safety on one side and speed on the other. Now let's see how they actually come together to solve a really common classic database problem: how to handle complex relationships in your data. So here's the puzzle.
A student can sign up for a bunch of different courses, right? And any given course is going to have a bunch of different students in it. We call this a many-to-many relationship. So how on earth do you link them together in a way that's both safe and fast? You can't just stuff a list of student IDs into the course table or a list of course IDs into the student table. That would be a complete mess and super inefficient. So the elegant solution is to create a third table right in the middle. It's often called a junction table. We'll call ours enrollments. And each row in this table does just one simple thing. It links one student ID to one course ID.
And this right here is where our two pillars meet perfectly. For safety, we use something called a foreign key constraint. That guarantees that you literally cannot enroll a student in a course that doesn't exist in the courses table. It's impossible. Then for speed, we put indexes on both the student ID and the course ID columns. That way we can find all the courses for a student or all the students in a course almost instantly. Safety and speed, working together.
And that brings us right back to where we started, to this central theme, the balancing act. Pretty much every decision you make when you design a database is some kind of trade-off between these two powerful forces.
In fact, entire families of databases are built specifically to prioritize one over the other. Your traditional SQL databases, like PostgreSQL or MySQL, are built from the ground up on that ACID model. They will always prioritize being consistent. But then you have this other world of NoSQL databases. Many of them follow a different model called BASE. It stands for basically available, soft state, and eventually consistent. And their main priority? Availability. They're willing to be a little bit inconsistent for a short period of time to make sure the system is always up and responsive.
And this isn't just, a stylistic choice. It's a fundamental law of distributed systems, something called the CAP theorem. As this note from Wikipedia says, a database has to lean one way or the other. It can't be perfectly consistent and perfectly available at the same time during a network failure. You have to choose. So really, it all boils down to this. We've seen how the ACID model gives you that rock-solid guarantee of correctness you would absolutely demand from your bank. But what if you weren't building a bank? What if you were building, say, a social media feed? In that world, maybe being available 100% of the time and feeling lightning fast is more important than showing every single like with perfect up-to-the-millisecond consistency. It's a choice you have to make: absolute safety or blazing speed. So which trade-off would you make for what you're building?